you are familiar with quantum algorithms that look like this, where we have a quantum circuit, essentially, that you're describing. Could you describe a quantum algorithm in a different language? Could I instead say that Grover's algorithm, this g applied k times, is just some e to the I h Grover times some time acting on some initial state? After all, you have just seen 2 lectures on adiabatic quantum computation. You have seen how an adiabatic model is able to utilize a shift from one Hamiltonian, the starting Hamiltonian, to a final Hamiltonian, and use that to simulate any quantum circuit. That was the whole point of the proof of universality of the adiabatic model of quantum computation. So you know in your minds that any quantum circuit can be now described by a suitably constructed Hamiltonian. This is slightly different. It doesn't have 2 Hamiltonians that you're shifting adiabatically between. But nevertheless, it should still be very appealing and natural. And I want to show you how this is possible here. So consider the following Hamiltonian. So we have a I think I'm going to leave out the 0 on the x naughts in the following, and you should be able to see where it arises naturally. Consider this Hamiltonian where you have 2 parts to it, and we'll take this Hamiltonian apart in just a moment. This part will be h1, h2. This will be the oracle, and this will be kind of the Grover part of the algorithm that knows nothing about what the answer is doing. But for a moment, give me the freedom to imagine what would happen if we evolved under this Hamiltonian, which is the sum of 2 parts. You won't actually have the sum. You'll have one Hamiltonian or the other Hamiltonian, since you have to pass off your state to the oracle. But I'll start with this combination for a moment. And I want to claim that if you can evolve under this Hamiltonian, you can solve the Grover problem. And the reason you can solve the Grover problem is actually kind of neat. Let me define, just like we did for the Grover algorithm definition, a picture where we look at the state orthogonal to that which is the answer state. And I'll call this y. So let y be equal to the superposition of all basis states minus the overlap. I'll define A in just a moment, normalized, where here psi x is equal to A. And since we're only considering a single marked item for simplicity, this is equal to 1 over square root of n, because there are n items in the superposition, only one of them is marked, and therefore A is just 1 over square root of n. Remember this geometric picture that we had for Grover's algorithm? We have some initial state, psi, which has an unknown overlap with x. That overlap is A. We don't know where it is. And then we have an orthogonal state. This is the state y I've defined over here. And then we have another state, which is the orthogonal complement of psi, which we won't care too much about for now. And Grover's algorithm rotated you in this 2-dimensional space. And what I now want to show you is that the Hamiltonian will do exactly the same thing. So let's take our Hamiltonian and rewrite it. In terms of x and y, because we want to write this in an orthonormal basis. After all, x and psi are not orthonormal with respect to each other, but we can certainly write this out in a orthonormal basis. So remember, psi is now going to be a superposition, which is ax plus square root of 1 minus a squared times y. And therefore, we can write this column vector and row vector. We have here a square root of 1 minus a squared, row vector a square root of 1 minus a squared, literally taking the bra and the ket here, and then plus xx, which is in this basis of x, y, x and y states, just a matrix with a single quantity in it, a 1. Now, if you work this all out and then rewrite this in terms of Pauli matrices, we love Pauli matrices, then it turns out to be something very simple. There will be a diagonal component, which is identity. You can see that this is appearing already over here. And then a times square root of 1 minus a squared times the Pauli X matrix, and a times the Pauli Z matrix. And I re-express this in a peculiar way because this is a unit vector. And having this form makes it very easy for us to exponentiate. So I can write e to the IHT directly, reading it off of this by knowing what happens with SU2. It is just going to be cosine of AT, because it's this is the amount of rotation. This is the axis of rotation. So with this amount, we stay unchanged. This is times identity, plus sine of AT times that unit vector over here, and an I. Square root of 1 minus a squared x plus a times z. By the way, this is a very neat trick which allows you to exponentiate any 2 by 2 matrix very rapidly. Just express the 2 by 2 matrix as identity plus some sum of Hermitian of Pauli matrices, and all matrices can be done that way because the Pauli matrices are a basis for Hermitian matrices. And then you can exponentiate the matrix immediately. So those of you in taking the Putnam exam can utilize quantum mechanics to get a faster result. It's more effective than quantum computation. OK, so if we now apply this to the initial state, e to the IHT times psi, remember psi is this x and y over here. Look at that. It's a 2 by 2 matrix, a rotation happening to a 2-component qubit vector. This is exactly like what we had before. And you can write this down easily, cosine AT times psi minus psi I times sine AT times x. OK, if you work this out. Excuse me, this is y. So we would like this term to be equal to 1. And so you choose t such that a times t is equal to pi over 2. So you've rotated all the way up to the answer. And this means that you want t to be equal to pi over 2a. Remember, a is down here, 1 over square root of n. So this is square root of n times pi divided by 2. Beautiful. Isn't that Grover's algorithm? And you got it without having to use any quantum gates whatsoever. It's all continuous mathematics. So you don't have to be a computer scientist. You can make progress just being a physicist doing simulations. Now, there's a catch, though. Remember, I had asserted that I was going to only use this sum of the 2 Hamiltonian terms as a crutch to start out with. But I have to go back and fix that crutch, because you're not actually given the sum of h1 and h2. You have to call h2 at a different time than you use h1. h1 is what you do. h2 is what the oracle is doing. And you don't have the degree of freedom of getting this sum for free. It comes at a cost.